Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to try and imagine something with me for a second. Imagine standing a full kilometer away from an object.
Right, which is, that's a massive distance.
Yeah, exactly. Just picture that immense distance. You're standing at one end of at a long, perfectly straight highway.
Okay.
And you're looking at something that is basically 10 football fields away.
So a distance that would take you, a good 10 or 15 minutes just to walk?
Exactly. It's a real trek. Now, from that incredible vantage point, I want you to imagine being able to perfectly see, and I mean visually resolve, something that is exactly 3.5 millimeters wide.
Oh, wow. 3.5 millimeter, it's roughly the width of maybe 2 stacked pennies.
Or like a single grain of rice.
Right, a grain of rice.
A grain of rice an entire kilometer away.
That is just mind-bending.
Right. But that is the exact level of visual sharpness, the sheer, optical perfection achieved by a newly developed Japanese X-ray space telescope.
Which is just an incredible engineering feat.
It really is. But here's the thing. Getting that perfect image required scientists to completely abandon everything we thought we knew about how telescopes actually work.
Oh, absolutely. They had to throw out the entire playbook.
You really did. They had to crossbreed their astronomical designs with the brutal physics of a particle accelerator.
Yeah.
They had to build a kilometer-long vacuum tube deep underground just to fake a single star.
Which is wild to even think about.
And then, after all that, they eventually strapped their creation to a rocket in the freezing wilderness of Alaska.
Just to see if it would survive.
Right. And the reason they went to all of these extreme, almost absurd lengths to literally shrink the entire future of space observation down to the size of a shoebox.
A shoebox. The journey to getting that technology into a shoebox is fundamentally a story about battling two of the most unforgiving hurdles in science.
Yeah, let's unpack that. What are we dealing with here?
Well, first, you are dealing with an incredibly hostile physical environment, outer space,
Right, space is not exactly friendly.
Far from it. You have the violent shaking of suborbital rocket launches, the hard vacuum, the extreme temperature swings.
It's basically a torture chamber for delicate equipment.
Exactly. And second, you are hunting the most elusive, difficult-to-capture targets in the known universe.
X-rays.
Yes, X-rays. High-energy X-rays do not behave like the visible light we are accustomed to seeing every single day.
They're a totally different beast.
They really are. They actively resist being caught. They resist being focused.
They just want to blast right through everything.
Right, and they require a complete reimagining of optical physics to even look at.
But the payoff for catching them is huge, right? It's the keys to the kingdom.
Oh, without a doubt.
We desperately want to catch these high-energy photons because they're the only way to really understand the universe's most violent, extreme temperature event.
Because we aren't trying to look at, quiet, peaceful dust clouds here.
No, we are chasing monsters.
That's a great way to put it. If you want to understand the calm, relatively cold universe, you look at visible light or infrared.
Right, the stuff Hubble or James Webb does.
Exactly.
Right.
But if you want to understand the true extremes of astrophysics, you absolutely must look at the X-ray spectrum.
So what exactly are we looking for? What makes these X-rays so special?
Well, there is a distinction we should establish right away between soft X-rays and hard X-rays.
Okay.
Because this new Japanese telescope, it's specifically hunting the hard ones.
Got it. So what's the difference?
Soft X-rays have lower energy levels, and they are emitted by things like the million-degree gas sitting in the corona of our sun.
Which is still incredibly hot.
Sure, yeah. But hard X-rays carry significantly more energy. They are the direct fingerprints of cataclysmic cosmic violence.
Cosmic violence. I love that term. What does that actually look like?
We are talking about enormous bursts of hard X-rays being violently expelled when magnetic field lines snap and reconnect during massive solar flares. Or we're talking about the detonation of dying stars. The supernovae that completely outshine their entire host galaxies.
Just unimaginably huge explosions.
Right. And perhaps most dramatically, hard X-rays are essentially the scream of superheated matter swirling violently around the event horizons of black holes.
Oh man, the stuff falling in.
Yes. It gets accelerated to millions of degrees by intense friction right before it crosses that threshold and just falls in forever.
So basically, the most dramatic, spectacular events in the cosmos are happening constantly, right over our heads.
All the time, 24/7.
But here is the massive physical barrier to actually seeing any of it. Earth's atmosphere completely, utterly absorbs these X-rays before they ever reach the ground.
Which, I have to point out, from a biological standpoint, is the only reason we are even alive to discuss it today.
Unquestionably, yeah. I mean, we'd be cooked otherwise.
Exactly.
I always think of our atmosphere as this incredibly dense, wraparound pair of heavy-duty, lead-lined sunglasses.
That's a really good analogy.
Because visible light trickles through just fine, right? Which is why our human eyes evolved to see that specific narrow band of the electromagnetic spectrum.
Right, we adapted to the light that actually makes it down here.
Exactly. But when it comes to ionizing radiation, the kind of high-energy X-rays that violently strip electrons away from atoms and, shatter DNA molecules, the atmosphere is an absolute vault.
It's a total lockdown. The nitrogen and oxygen molecules high above us intercept those X-ray photons through a process called photoelectric absorption.
Okay.
And it is absolutely essential for keeping the fragile biology of Earth safe from being sterilized by cosmic radiation.
So great for not getting vaporized.
Very great.
But it is incredibly frustrating if you are an astrophysicist trying to look at the blinding flashes of a solar flare.
Oh, it's maddening. And the historical context of that frustration is actually super fascinating when you think about the timeline of astronomy.
How so?
Well, for thousands of years, human beings looked up at the night sky, charted the stars, tracked the planets.
Like the ancient Greeks, the Mayans?
Right. And they genuinely believed they were seeing the whole picture of the universe.
Because that's all they could see.
Exactly. But they were completely blind to the high-energy reality. They were only seeing that tiny sliver of the electromagnetic spectrum that makes it through the atmospheric sunglasses.
So the entire X-ray universe, the violent, churning, high-energy cosmos, was entirely invisible to us.
Completely invisible. It wasn't until the mid-20th century, specifically around the late 1940s and early 1960s.
Wait, that recently?
Yeah. That was when scientists first put rudimentary Geiger counters onto captured V-2 rockets and sent them above the atmosphere.
Wow. So they literally had to shoot a rocket up there just to realize it was happening.
Right. And that was the exact moment we realized the sky wasn't just twinkling peacefully, it was glowing and pulsing with intense X-ray radiation.
That must have been a mind-blowing discovery.
It changed everything. Because to understand the fundamental laws of physics, gravity, and magnetism, you really have to study these high-temperature processes.
So imagine knowing that the most spectacular fireworks show imaginable is happening right above your head, 24 hours a day.
All right.
But you are permanently trapped inside a house with no windows, sitting behind this impenetrable curtain of air.
That is exactly the dilemma. Ground-based X-ray astronomy is not just, difficult. It is a physical impossibility.
Because the atmosphere acts like a solid brick wall for those high-energy photons.
A total brick wall.
So because observation from the surface is a complete non-starter, you are forced to bypass the atmosphere entirely.
You have to go to space.
You have to. And historically, scientists started with high-altitude weather balloons, trying to get just above the thickest part of the air.
Yeah, that was step one.
Then they moved to suborbital sounding rockets and eventually the massive permanent satellites we have up there today.
But here's the catch. Just getting your instrument above the atmosphere is only solving half the problem.
Right.
The real nightmare, the true engineering paradox that basically melted my brain when I first understood it, is trying to actually catch and focus a hard X-ray once you're up there in the vacuum of space.
Because the moment you try to build a telescope for X-rays, you have to completely discard the everyday intuitive understanding of how mirrors work.
You really do.
Because think about it. When you picture a telescope, you picture a large, curved piece of glass coated in a highly reflective metal.
Right, like a big satellite dish for light.
Yeah, like a massive, precisely engineered version of the mirror in your bathroom.
Exactly.
Light hits the curved surface, bounces off, and focuses perfectly onto a single point where an eyepiece or a digital sensor sits.
That's standard optics.
You point a regular curved mirror at a distant star, and boom, you have an image.
But you absolutely cannot do that with X-rays. And the underlying physics of why you can't is crucial to understanding this Japanese team's breakthrough.
So break that down for us. Why doesn't a normal mirror work for an X-ray?
Well, normal mirrors rely on visible light photons, which have relatively long wavelengths and low energy.
Okay.
When visible light hits the atomic structure of a silver or aluminum coating, it interacts with the electron clouds of those atoms and just bounces right back.
It reflects.
Right. But X-rays, especially hard X-rays, carry an immense amount of energy. Their wavelengths are incredibly short.
So they don't bounce.
No. If you point a normal dish-shaped mirror directly at a black hole emitting hard X-rays, the photon doesn't bounce. It punches straight through the mirror.
It just blasts right through the glass.
Straight through. Or it gets completely absorbed by the atomic structure of the mirror itself.
Wow.
It's the fundamental defining property of high-energy photons. They penetrate matter.
I mean, that's exactly why we use them for medical imaging, right?
Yeah.
To look at broken bones inside the human body.
Exactly. They pass right through the soft tissue because the carbon and water molecules in our flesh don't have the density to stop them.
The bones are dense enough to cast a shadow, but the flesh isn't.
Right. So in an astronomical context, if you build a traditional dish-shaped parabolic mirror and fly it above the atmosphere, the high-energy X-rays from a solar flare will just blast straight into the dish and vanish into the metal.
You get nothing.
You get zero reflection, zero focus, and therefore absolutely no data.
So how do you fix it? How do you make something that just wants to punch through a wall actually bounce off it?
It's a geometry problem.
And the analogy that really clarifies this geometry for me is the skipping stone.
Oh, that's a perfect analogy.
Right. Think about standing at the edge of a completely still pond with a rock in your hand.
Okay.
If you stand right over the water and throw the rock straight down, which is the equivalent of an X-ray hitting a normal mirror face on what happens.
The rock just breaks the surface tension instantly and sinks right to the bottom.
Exactly, it sinks.
Mm-hmm.
But if you want that rock to bounce, if you want to skip the stone across the surface of the pond, you have to change your geometry.
You have to get down low.
You have to get down low to the water and throw the rock at an incredibly shallow, almost perfectly horizontal angle.
You have to make it graze the surface.
Yes, graze it.
And the physics concept governing this in optics is literally called grazing incidence.
Grazing incidence. Okay, so how does that work with X-rays?
Well, the refractive index of all materials for X-rays is actually slightly less than 1.
Which means what exactly?
It means that unlike visible light, which bends when it enters glass, X-rays exhibit a phenomenon called total external reflection, but only, and this is a huge, only under extremely specific conditions.
Let me guess, the skipping stone conditions.
Exactly. The only physical way to make a hard X-ray reflect off a surface without being absorbed is if it strikes that surface at a microscopic grazing angle.
How microscopic are we talking?
We are talking about an angle of incidence that is often less than a single degree.
Less than 1 degree.
Yes. It has to skim the metallic surface, exactly like you're skipping stone skimming the water.
Wait, okay, hold on. If the X-rays are only skipping off the very edges of this surface at a 1 degree angle, doesn't that mean the actual, catching area of the telescope is almost non-existent?
Yes. You hit the nail on the head.
Because if you point a flat cylinder at the sky, the frontal area intercepting the light is just the razor-thin rim of the cylinder.
Right.
Aren't you basically throwing away 99% of the photons you just flew all the way to space to catch?
You absolutely are, and you are hitting on the exact critical flaw of grazing incidence optics.
It seems so inefficient.
It is. The effective collecting area is abysmally small compared to a standard telescope because you can only catch the photons that hit the extreme inner edge of the mirror at that sub-1 degree angle. The vast majority of the X-rays just pass straight down the empty middle of the tube without touching anything.
So they just fly straight through the hole.
Yeah, or they hit the outside of the tube and are totally lost.
Wow.
This is exactly why Dr. Ikuyuki Mitsuishi, the project leader from the Graduate School of Science at Nagoya University, described their mirror specifically as a very precise funnel.
A funnel. That makes so much sense. Not a dish, not a bowl. A hollow cylinder that narrows.
Exactly.
The X-rays enter the open top of the barrel, skip off these smoothly sloped inside walls at that tiny grazing angle, and get funneled down into a concentrated point where a digital detector sits at the bottom.
But, and this is a massive but, the requirement of that incredibly shallow angle creates an engineering and manufacturing nightmare that basically borders on the impossible.
Because the tolerances have to be so tight.
Beyond tight. Because the reflection angle is so shallow, the margin for physical error on the surface of that funnel is effectively zero.
Zero margin for error.
We are not talking about millimeter precision here. We are not even talking about micrometer precision.
Then what are we talking about?
We are operating in the realm of nanometer level precision.
Nanometer?
Yes. Dr. Mitsuishi emphasized that if any part of the interior of this funnel is even slightly misaligned, or if the surface texture is slightly rough at a microscopic level, the X-ray photons will not bounce toward the focal point.
They'll just scatter everywhere.
They will scatter wildly, they will miss the tiny digital detector completely, and the million-dollar image you just went to space to capture becomes nothing more than a useless, blurry smudge of static.
Just to establish what nanometer precision actually looks like for you guys listening, a nanometer is 1/1000th of a meter.
Right. It's almost unimaginably small.
A standard human hair is roughly 80,000 to 100,000 nanometers thick.
Wow. Yeah.
So we are talking about shaping and polishing the interior wall of a metallic barrel to a degree of absolute smoothness that is tens of thousands of times smaller than the width of a single hair.
And achieving that kind of surface smoothness in a sterile, pristine, temperature-controlled, vibration-isolated optical laboratory on Earth is a monumental undertaking on its own.
Right, just doing it on a desk is hard enough.
But this is where the aerospace variable completely ruins your day.
Oh, no.
Because this is not a lab experiment meant to sit nicely on a heavy granite table. This is a space telescope.
Right, so you spend months, maybe years, building this flawless, nanometer-precise optical masterpiece. And then what is the very next step?
You put it on a rocket.
You strap it to the top of a giant metal tube filled with highly explosive rocket fuel, and you basically detonate it.
Exactly. The agonizing reality of aerospace engineering is that you must subject incredibly delicate instruments to pure, unadulterated physical brutality.
So counterintuitive.
During a rocket launch, the payload inside the fairing experiences a gauntlet of destructive forces.
Like what is the telescope actually going through?
First, there are the immense G-forces of acceleration, physically crushing down on the structure as it blasts off the pad.
Right, just the raw speed.
Then you have massive thermal expansion and contraction as the rocket moves from the ambient temperature of launch pad, pushing through the friction of the atmosphere and into the freezing vacuum of space.
So the metal is heating up and shrinking down rapidly.
Yes. But the most destructive force for optics, believe it or not, is acoustic.
Sound. Sound destroys telescopes.
Oh, absolutely. The acoustic shockwaves generated by the rocket engines are so phenomenally loud, often exceeding 140 to 150 decibels.
That's like standing inside a jet engine.
It is. The sound waves alone can literally shatter rigid materials. The physical vibrations are just bone-rattling.
It's the aerospace equivalent of taking a finely tuned, meticulously balanced Swiss watch, throwing it into an industrial paint shaker, turning it on high for 10 minutes, and expecting it to keep perfect time when you take it out.
That is exactly what it is. And after all of that chaotic violence, when the fairing finally opens in the dead silence of space, that nanometer precision has to be completely, utterly intact.
If a single piece of the internal mirror assembly is shifted by, the width of a bacteria?
The optics are ruined.
The optics are ruined and the mission just fails.
Complete failure. Which brings the engineers to a very harsh realization.
Which was?
The astronomers at Nagoya University understood that traditional telescope manufacturing techniques were simply not going to survive this environment.
Right, because how do you traditionally make these things?
Historically, if you wanted to build a grazing incidence X-ray telescope, you would grind curved pieces of glass or metal, and then you would physically bolt those different curved segments together to form the funnel.
Oh, I see. You build it in pieces.
Right. But a multi-part mirror inherently has joints, it has seams, it relies on brackets, epoxy, and microscopic screws.
And under the extreme acoustic stress and vibration of a rocket ascent, seams are fatal.
Fatal. Where there is a joint, there is the potential for movement.
A seam is basically a structural vulnerability waiting to happen.
Exactly. Moving parts shift during launch. If your mirror shifts, your focal point shifts.
And even beyond the structural weakness, seams are the mortal enemy of grazing incidence optics from a pure physics standpoint, aren't they?
Oh, entirely. If you construct a cylindrical funnel out of, say, 4 separate curved pieces of metal, there will always inevitably be a microscopic gap or a raised ridge where those pieces meet.
Because nothing is truly perfect when bolted together.
Right. So when a high-energy X-ray photon skips along the surface and encounters that seam, it doesn't just gracefully hop over it.
It trips?
It trips. It hits the ridge and deflects randomly. It scatters. A seamed mirror bleeds light and just completely destroys your image resolution.
So the Nagoya team needed a mirror with no moving parts, no brackets, no bolts, and absolutely no seams.
None.
They needed a single, continuous, perfectly smooth, monolithic shell.
A single piece of metal.
But they also quickly realized they couldn't just call up a traditional commercial telescope manufacturer to build it, right?
No, because traditional lens grinders don't make seamless metal funnels. It's not in their wheelhouse.
So to solve an optical problem this complex, they had to step entirely outside of their own field of astronomy.
They did. They needed the hyper-specialized precision of particle physicists.
Which is wild.
It is. They basically had to ask themselves, who on Earth is already spending billions of dollars to build incredibly precise, indestructible, perfectly smooth funnels for high-energy X-rays?
And the answer was not an observatory.
No, the answer was Spring 8.
Wait, okay. You're telling me telescope engineers couldn't figure out how to build a space telescope, so they went to the people who smash subatomic particles together?
I know it sounds like science fiction, but yes, that's exactly what happened. Spring 8 is a massive, world-renowned research facility located in Hyogo Prefecture, Japan.
Okay.
It is not an astronomical observatory. It is a synchrotron radiation facility.
A synchrotron?
Yeah. It is one of the most powerful and advanced X-ray research installations on the entire planet, characterized by this massive circular ring measuring nearly 1.5 kilometers in circumference.
What exactly happens inside a 1.5-kilometer ring? Like, what are they doing in there?
Particle physicists take electrons, inject them into a massive circular vacuum tube, and use incredibly powerful electromagnets to accelerate those electrons until they are moving at very nearly the speed of light.
Which is fast.
Unbelievably fast. Now, according to the laws of electrodynamics, when you take a charged particle moving at relativistic speeds and you force it to bend its path to travel around a curve rather than in a straight line, it sheds energy.
It bleeds it off.
Right. It bleeds off that energy in the form of incredibly intense, bright, and highly focused beams of X-rays.
Oh, I see.
And that brilliant light is called synchrotron radiation.
And researchers from all over the world travel to Spring 8 to tap into those intense X-ray beams, right?
They do.
They use them to map the atomic structure of new pharmaceutical drugs, to analyze the molecular weaknesses of advanced aerospace alloys, to peer inside the chemical reactions of next-generation batteries. But here is the massive catch. To actually utilize those blindingly powerful X-ray beams in their laboratories, the Spring 8 physicists had to figure out how to physically corral and focus them.
Because you can't just let that kind of beam fly around the room.
Exactly. They had to invent their own ultra-precise mirror technologies just to safely bounce the X-rays generated by their own particle accelerator into their experimental stations without melting their equipment or losing the beam.
And this is where the cross-disciplinary brilliance of the project truly shines.
It's such a cool collaboration.
It really is. You have the astronomy team from Nagoya University who deeply understood the complex optical mathematics required to image the sun.
And who knew exactly what kind of brutal payload stresses a rocket launch would inflict.
Right. And they teamed up with the synchrotron radiation community at Spring 8, who possessed the bleeding-edge proprietary manufacturing technology required to physically craft these exotic, seamless mirrors.
It is basically a flawless marriage of space astronomy and high-energy particle physics.
It is. So they join forces. And they aren't grinding massive blocks of glass.
No.
They use a proprietary manufacturing technique perfected at Spring 8 called precision electroforming.
Precision electroforming.
Yes.
Now, electroforming is a word that gets thrown around, but how do you actually grow a seamless metal mirror from scratch? What does that mean?
It is essentially 3D printing at an atomic scale.
Atomic scale 3D printing.
Okay. The electroforming process completely inverses the concept of carving a mirror.
Oh.
You don't start with a block of metal and hollow it out.
Right.
Instead, you start with a master mold, which is called a mandrel.
A mandrel.
Yeah. This mandrel is a solid cylinder of metal, usually aluminum or a specialized alloy, that has been machined and polished to absolute sub-nanometer perfection.
So it's perfectly smooth.
Completely. And the outside of the mandrel is shaped exactly like the negative space of the empty funnel they want to create.
Ah, I get it. So you spend all your time polishing the solid block, not the hollow tube.
Precisely. It is much easier to polish the outside of a solid object than the inside of a narrow tube.
Oh, that makes total sense.
So once the mandrel's exterior is flawlessly smooth, they submerge it into an electrochemical bath rich in dissolved nickel ions.
Okay, so it's taking a bath in nickel.
Right. By running a highly controlled electrical current through the bath, the positively charged nickel ions are drawn to the surface of the mandrel.
Like a magnet.
Exactly like that. They deposit themselves onto the mold, atom by microscopic atom, layer by incredibly thin layer.
Wow.
The nickel slowly builds up, creating a metallic shell that conforms perfectly down to the atomic level to the nanometer smooth surface of the mandrel.
And because the nickel atoms are bonding to each other molecularly as they deposit, there are no seams.
None.
There are no joints. It is a single, continuous crystalline structure of pure metal.
Yes. And once the nickel shell has grown thick enough to be structurally sound, they cool the entire assembly down.
Okay, why do they cool it?
Because the aluminum mandrel and the nickel shell have different coefficients of thermal expansion.
Oh, I see.
The mandrel shrinks slightly more than the nickel when cooled, allowing them to carefully slide the hollow nickel shell right off the mold.
That is so clever.
Yeah.
And what you are left with is the ultimate X-ray funnel.
The ultimate funnel.
The specific mirror shell they manufactured for this mission is roughly 60 millimeters across and 200 millimeters tall.
So it's pretty small.
Yeah, it's lightweight, it is incredibly rigid, and because it is seamless, it has absolute optical purity.
And crucially, a vastly superior chance of surviving the acoustic paint shaker of a rocket ascent.
Right. But the shape of this funnel is not just a simple, straight-walled cone, is it?
No, not at all.
The geometry of the interior wall is mathematically complex. The entire mirror assembly, which stands about 250 millimeters tall when fully mounted in its housing, actually utilizes two distinct, highly specific geometric curves to focus the light.
Right. And this is known in physics as Volter optics.
Volter optics, okay.
Yeah. Yes, specifically Volter-type eye optics, named after the German physicist Hans Volter, who first proposed the design way back in the 1950s.
So it's an old theory, finally perfectly realized.
Exactly. The electroformed nickel shell is divided into two sections. The upper section of the mirror features a paraboloidal curve, while the lower section features a hyperboloidal curve.
Wait, if the goal is just to skip the X-ray down to the bottom of the funnel, why on earth do you need two completely different mathematical shapes?
It seems overly complicated, right?
Yeah. Why wouldn't a single smooth curve work?
It all comes down to correcting optical aberrations. If you build a funnel using only a single parabolic curve, you run into a massive problem called coma aberration.
Coma aberration.
Yes, which violates what physicists call the Abbe-Sine condition.
Okay, let's ground that. What does a coma aberration actually do to the image of a star? What would I see?
If an X-ray enters a single curve funnel slightly off-axis, meaning it doesn't come straight down the absolute dead center of the barrel.
Which it almost never will, right?
Exactly. The single bounce will cause the focal point to smear. Instead of seeing a sharp, tiny dot representing the star, you will see a blurred shape that looks like a comet with a trailing tail.
Oh, I've seen pictures like that.
Right. That tail is the coma aberration. It destroys the high-resolution data you are trying to collect. Hans Volter realized that to properly focus grazing incidence X-rays to a flawlessly sharp point across a wider field of view without massive distortion, skipping the photon just once isn't enough.
You have to bounce it twice.
Exactly. You bounce it twice to correct the optical path length.
So walk me through the path of a photon here.
Okay, the high-energy X-ray enters the top of the telescope, skips off the upper paraboloidal section, travels a few centimeters, then hits the lower hyperboloidal section, skips off again, and finally angles perfectly down into the focal point where the detector sits.
It's like a perfectly banked double shot and pool.
It really is. The two highly specific curves work in tandem to cancel out the optical distortion.
And the sheer brilliance of the Spring 8 electroforming process is that it allows them to grow this incredibly complex two-stage geometric curve perfectly, seamlessly, inside a single solid piece of nickel.
It is an absolute masterpiece of engineering.
It really is.
Yeah.
So the Nagoya and Spring 8 teams have successfully built this indestructible, seamlessly grown, dual-bounced Volter funnel.
The hardware is ready.
The hardware is ready. But here arises the next massive logistical nightmare.
Oh, yeah, because you can't just trust it without checking it.
Right. Before you can strap this multi-million-dollar piece of custom hardware to a rocket and hurl it into the upper atmosphere, you have to verify that it actually works.
You have to test it on the ground.
And testing a high-resolution space telescope on Earth requires you to simulate the exact conditions of outer space.
Right.
You have to fake a star.
Which sounds conceptually straightforward until you look at the geometry of starlight.
Exactly. When we look up at a star in the night sky, we are looking at an object that is trillions of miles away.
Just incomprehensibly distant.
Right. Because the light source is located at a distance approaching infinity from our perspective. By the time those specific light rays travel across the vacuum of space and reach Earth, they are no longer spreading out in all directions.
The geometric spread is so minimal that the rays are essentially perfectly, completely parallel to one another.
Right. Starlight arrives at our atmosphere as parallel rays. And the complicated paraboloid hyperboloid geometry of the Wolter mirror we just discussed is specifically mathematically designed to take parallel rays of light and fold them down into a single microscopic point.
Right.
But if you try to test this mirror in a normal, standard-sized laboratory room, say, by taking an X-ray emitter and placing it 10 or 20 feet away from the funnel.
The geometry completely fails.
Because it's too close.
Way too close. The X-rays coming out of a machine from 10 feet away are still spreading out violently. They're diverging rays.
So if you point the telescope at a lab source 10 feet away, the diverging X-rays hit the interior walls of the funnel at the wrong angles.
Completely the wrong angle.
The dual bounce mechanism won't function correctly, and the resulting image on the detector will be a blurry mess.
Right. And the worst part is the engineers wouldn't know if the image was blurry because the electroform mirror was physically flawed, or simply because the test environment was geometrically incorrect.
So you can't trust the test.
You can't. To truly recreate the parallel rays of deep space starlight on the ground, you need immense, almost absurd distance between the light source and the mirror.
Which is exactly why the team engineered a testing system at the Spring 8 facility that is staggering in its scale.
It's massive.
To force those diverging X-rays to mimic the parallel nature of starlight, they had to place their artificial star, a microscopic X-ray point source, a full 900 meters away from the telescope mirror.
900 meters, almost a full kilometer.
This brings us right back to the visual we started with.
A highway.
Yes. Imagine a corridor nearly a kilometer long. At one far end of this massive hallway, you mount the 60-millimeter wide telescope mirror.
Okay.
At the absolute other end, you place the X-ray source.
And we must emphasize the scale of that source, too.
Right. It's not a floodlight.
No. To test the extreme resolution limits of the mirror, you cannot use a massive blinding source. The X-ray point source they used at Spring 8 was a mere 10 micrometers across.
A human hair is roughly 80 to 100 micrometers thick.
Yeah.
This artificial star they built is a fraction of the width of a single human hair.
It's basically a speck.
The alignment challenge alone is mind-boggling. They had to take a microscopic, invisible beam of high-energy radiation and aim it perfectly down a 900-meter corridor to strike a target the size of a coffee mug.
But the geometry works.
It does.
Yes. By traveling that extreme 900-meter distance, the widely diverging rays spread out so massively that the tiny, specific fraction of photons that actually manage to enter the 60-millimeter opening of the mirror are, for all practical mathematical purposes, perfectly parallel.
Wow.
It flawlessly mimics the physics of incoming starlight.
But wait, the atmosphere ruins everything again, doesn't it?
Oh, of course it does.
No, you can't just fire hard X-rays down a regular hallway for a kilometer. The air in the room will absorb and scatter the beam.
Yeah, if you attempted to fire a hard X-ray beam through 900 meters of standard atmospheric air, the photoelectric absorption and Compton scattering caused by the nitrogen and oxygen molecules would completely degrade the beam.
It would just get eaten up by the air.
Exactly. By the time it reached the mirror, there would be practically no photons left to reflect.
So to solve the air problem, they enclosed the entire 900-meter beam path inside specialized vacuum tubes.
That is just wild to think about.
They constructed a kilometer-long vacuum chamber underground at the Spring 8 facility, pumping out all the atmosphere, strictly to test a piece of metal the size of a mug.
It highlights the extreme lengths required to push the boundaries of modern astrophysics. You have to move mountains just to test your gear.
And the results they gathered from this subterranean vacuum test were spectacular, right?
Oh, a total success.
The digital detectors captured color-coded X-ray images, proving that the Wolter optics were successfully bouncing the high-energy photons exactly as simulated.
focusing them down into a spectacularly sharp central point.
They achieve that mind-bending resolution we talked about at the beginning. The ability to visually resolve an object 3.5 millimeters wide from a full kilometer away.
Which is just incredible. But the scale of this test facility brings up an incredibly important point regarding the broader impact of this research.
Right, because this massive 900-meter vacuum tube wasn't just a temporary stunt hastily assembled for this one specific telescope shell, was it?
Not at all. Rito Fuji, the first author of the research study and a former master student deeply involved in the project, articulated the true lasting value of what they constructed at Spring 8.
And what is that lasting value?
This isn't just a win for Nagoya University. This specific beamline setup is the very first ground-based system anywhere in the world capable of accurately evaluating the performance of high-resolution X-ray space telescopes, specifically operating at hard X-ray energy levels.
And the most vital part of that achievement is that the facility is now available to the global scientific community.
Exactly. It's a resource now.
Any university or space agency developing similar high-energy grazing incidence technology can now bring their mirrors to Hyogo, put them in the 900-meter vacuum tube, and definitively prove their hardware functions before spending hundreds of millions of dollars securing a rocket launch.
It is a massive infrastructural contribution to global astronomy.
So with the 900-meter ground test, a resounding quantified success, the electroformed mirror was declared flight-ready.
It was time to go.
The geometry held. The resolution was verified. Now it was finally time to leave the pristine, temperature-controlled safety of the Spring 8 laboratory and head to the launch pad.
It was time for the FLXSI-4 mission.
In April of 2024, the team packed up their seamless, electroformed marvel, crossed the Pacific, and transported it to the freezing, desolate launch pads of the Poker Flat Research Range in Alaska.
Right.
Now, when most people think of a space launch, they picture Cape Canaveral.
Florida.
Yeah.
Sun, palm trees.
Right. They picture a massive SpaceX Falcon 9 or an Atlas V rocketing a school bus-sized satellite into permanent orbit around the Earth, where it will operate for 20 years.
But FOXSI-4 was a sounding rocket mission.
Right. What fundamentally separates a sounding rocket from the orbital launches we usually see on the news?
It is a completely different operational paradigm. An orbital launch vehicle uses hundreds of tons of liquid fuel to push a payload up above the atmosphere.
Okay.
And then, critically, it must accelerate that payload horizontally at thousands of miles per hour.
Right, because you have to stay up there.
Orbit is essentially moving sideways so incredibly fast that as gravity pulls you down, the curvature of the Earth falls away beneath you at the exact same rate.
You're constantly falling and constantly missing the ground.
But a sounding rocket doesn't do that.
What does it do?
A sounding rocket doesn't have the immense fuel capacity required to achieve horizontal orbital velocity. A sounding rocket is essentially a suborbital parabolic shot.
Like an arc.
Right. It fires straight up into the sky, breaches the atmosphere, reaches the vacuum of space, and then almost immediately falls straight back down to Earth.
It is the aerospace equivalent of throwing a baseball straight up into the air.
Exactly. It carries the scientific instruments briefly into space, giving them a few minutes of weightlessness and a perfectly clear, unobstructed view of the cosmos above the atmospheric shielding.
Okay.
And then the entire payload descends on a parachute to be recovered in the Alaskan wilderness.
So it is an unbelievably harsh, incredibly fast-paced environment.
Highly stressful.
Because when you launch a satellite like the James Webb Space Telescope, engineers spend months carefully unfolding mirrors, calibrating sensors, and running diagnostics before taking a single picture.
They take their time.
On a sounding rocket, you don't have months. You have minutes.
On a typical sounding rocket flight profile, the instruments might only be above the atmosphere and capable of observation for about 5 to 10 minutes before gravity pulls them back down into the air.
5 to 10 minutes. That is a tight window.
It's incredibly tight. And the FOC-XSI program, which stands for Focusing Optics X-ray Solar Imager, is a collaborative international experiment specifically engineered for this rapid-fire, high-stakes observation window.
So what are they trying to look at so quickly?
Its primary scientific objective is to capture high-resolution, hard X-ray images of the sun's corona, to study the mechanics of solar flares, and to understand how magnetic energy is violently converted into thermal energy.
Okay, wow.
The program has been running since 2012, incrementally flying better and better instruments with each iteration.
And on April 17, 2024, FOXSI-4 successfully blasted off from the Poker Flat Range in Alaska, carrying a payload of 7 different X-ray telescope modules.
Yep.
One of those 7 was the seamless electroformed nickel funnel developed by the cross-disciplinary team from Nagoya University and Spring 8.
And the historical and emotional weight of that specific launch really cannot be overstated.
I can't even imagine.
Dr. Mitsuishi and his dedicated team of graduate students were physically present at the Alaskan range to watch the countdown.
Standing out there in the freezing cold.
Standing in the cold, feeling the deafening, bone-rattling roar of the solid rocket motors vibrating in their chests.
Just hoping their mirror holds together.
Right. They were watching the absolute culmination of years of theoretical optical physics, particle accelerator engineering, and relentless ground testing blast off into the sky.
It was a huge milestone moment. It was the very first time a domestically developed Japanese high-resolution X-ray telescope had ever flown on an international-sounding rocket mission.
And the technology delivered exactly as promised.
It survived.
It survived. The acoustic shock waves and the extreme G-forces of the launch ascent did not destroy the optics.
The lack of seams saved it.
Absolutely. The seamless nickel shell, grown atom by atom in an electrochemical bath, held its shape perfectly.
So what did they see?
While the payload was coasting above the atmosphere in its brief window of microgravity, the telescope pointed at the sun and successfully observed a solar flare in progress.
A live solar flare.
Yes. The dual-bounce Wolter geometry functioned flawlessly in a vacuum, focusing the high-energy, hard X-ray photons emitted by the snapping magnetic field lines exactly as the 900-meter ground test predicted it would.
That is just such a massive triumph.
It is.
But the defining characteristic of a truly great scientific team is that they never just pop the champagne, declare total victory, and move on.
No, they immediately start looking for what went wrong.
Exactly. Despite this massive historic success, the moment they recovered the payload and downloaded the telemetry, they immediately began tearing apart the data to find the flaws.
They wanted to know why the image resolution wasn't even more perfect.
That relentless, critical pursuit of incremental improvement is the fundamental engine of the scientific method.
It really is.
So by heavily scrutinizing the performance data and the image resolution captured during the FOC SI-4 flight, the Nagoya team actually identified the primary limiting factor that prevented the mirror from achieving even sharper theoretical perfection.
They found the weak link.
And what was the culprit? Did the structural housing bend under the G-forces? Did the digital detector fail?
No. The overall structure remained entirely sound. The limitation came down to the absolute microscopic boundaries of the electroforming manufacturing process itself.
Really? The atom-by-atom printing wasn't good enough.
They discovered that there were still infinitesimally tiny imperfections along the internal length of the nickel mirror surface.
How tiny are we talking?
We are not talking about major structural warping or visible seams. We are talking about microscopic textural variations at the atomic lattice level.
Wow.
Angstrom-level roughness in the crystalline structure of the nickel that caused a small fraction of the hard X-rays to scatter slightly more than the theoretical physics models predicted.
So even after utilizing bleeding-edge particle accelerator technology to grow a mirror atom by atom, the universe still demands an even smoother surface to properly reflect its highest energy light.
But identifying the exact nature of the problem is the most important step in science.
Right, because now you can fix it.
Because they isolated the scattering effect to atomic-level surface roughness, they now possess a perfectly clear, actionable target for improvement.
They know what to tweak.
They know exactly what parameters of the electrochemical bath, perhaps the deposition rate, the temperature, or the ion concentration, they need to refine in the electroforming process to make the next iteration of the mandrel and the shell even smoother.
And they are already back in the laboratory working on it.
Oh yeah, they didn't waste any time.
Because a newly refined, improved version of this seamless telescope is already manifested and scheduled to fly on the upcoming FOC SSI-5 mission slated for 2026.
Which is coming up fast.
So we have a fully validated manufacturing process, a successful suborbital launch, a working high-resolution telescope, and a concrete roadmap to make the next one even sharper.
It's an incredible timeline.
But refining the surface texture to get a slightly clearer picture of a solar flare isn't the ultimate endgame of this project.
No, not at all.
The true ambition of the Nagoya team is vastly more expansive. The real goal is to take this validated, highly efficient, seamless mirror technology and use it to forcefully shrink the entire paradigm of space exploration.
We are talking about facilitating a massive paradigm shift in astrophysics.
How so?
The transition from relying exclusively on colossal, multi-billion-dollar government observatories to deploying agile, highly accessible, inexpensive fleets of tiny satellites.
Let's talk about that future, the shoebox future of astronomy.
I love that phrase.
When the average person thinks of space telescopes, they picture the Hubble Space Telescope or the James Webb Space Telescope.
Right, the big ones.
These machines are massive, school bus-sized behemoths. They weigh several tons.
They are huge.
They require decades of international political maneuvering to fund, billions of dollars to design, and the largest, most expensive orbital rockets on the planet just to launch them.
And because these monolithic observatories are so astronomically expensive and exceedingly rare, the observing time on them is one of the most fiercely competitive resources in the scientific world.
I can imagine. Everyone wants a turn.
An astrophysicist will literally wait years, sometimes staking their entire academic career, just to secure a few precious hours of time to point one of these giant telescopes at a specific galaxy or black hole of interest.
But the Nagoya University team wants to completely upend that monopolized model.
They want to blow it wide open.
Their long-term objective is aggressive miniaturization. They want to take this lightweight, highly efficient, seamlessly electroformed X-ray funnel and scale it down to the point where the entire telescope assembly, the mirror, the housing, the digital detector, the power source, and the telemetry transmitter fits entirely inside something called a CubeSat.
If we break down the dimensions of a CubeSat, the contrast against something like Hubble becomes absolutely staggering.
What are the dimensions?
A CubeSat is a highly standardized class of nanosatellites. The base structural unit, known as a 1U, is a cube measuring exactly 10 by 10 by 10 centimeters.
10 centimeters, that's tiny.
You can stack a few of these standardized units together to create a 3U or a 6U satellite, but fundamentally we are talking about launching a fully functional deep space observatory that is roughly the physical size of a shoebox.
A shoebox. Compare that to a machine the size of a yellow school bus.
The difference is night and day.
The economic implications are massive because in aerospace engineering, mass is money.
Mass is absolutely money.
Every kilogram you try to lift out of Earth's gravity well costs tens of thousands of dollars.
The beauty of the CubeSat standardization is that they are phenomenally cheap to construct, often utilizing off-the-shelf commercial electronics for their bus systems, and they are incredibly cheap to launch.
Because they just hitch a ride.
Right. Exactly. Because they are so small and lightweight, they don't need a dedicated rocket. They can simply hitch a ride as secondary payload ride shares on rockets that are already going to orbit to deploy larger commercial communications satellites.
But up until this specific breakthrough in Japan, the idea of putting high-resolution, hard X-ray optics onto a CubeSat was basically considered science fiction.
Oh, totally. People thought it was impossible.
Because the traditional bolted-together glass mirrors were too heavy, the optics were too physically complex, and the required focal lengths were too large to fit into that tiny 10-centimeter form factor and survive the launch environment.
Exactly. High-resolution X-ray optics have never successfully flown on CubeSats. It was physically prohibitive.
But this spring-8 electroformed nickel funnel fundamentally alters the equation.
It changes everything.
The nickel shell is incredibly lightweight. Because it is a single seamless structure, it is physically robust enough to survive launch without massive, heavy structural support brackets. And most importantly, its optical efficiency and ability to correct coma aberrations are so high that even a vastly scaled-down version of the Wolter funnel can catch enough photons to generate highly meaningful, publishable scientific data.
So if they successfully integrate these funnels into a 10-centimeter box, what does this actually mean for the future of science? Why does the shoebox future of X-ray astronomy matter so much?
Because it completely democratizes access to the extreme universe.
Democratizes space. I like that.
It takes the ability to observe the most violent, fundamental, high-energy processes in the cosmos out of the exclusive, monopolized hands of massively funded, multi-decade government agency projects, and it puts that capability directly into the hands of a much broader, more diverse scientific community.
Imagine a standard university physics department, or even a well-funded graduate program, being able to design, physically build, and launch their own dedicated high-resolution X-ray space telescope in the span of 3 or 4 years.
Or a tiny fraction of the cost of a traditional satellite.
Right. The scientific yield changes dramatically when you shift from a monolithic model to a swarm model.
A swarm model. That sounds so cool.
Instead of relying on one giant telescope attempting to look everywhere at once and missing things because its schedule is booked years in advance, universities could launch a swarm of dozens of specialized, shoebox-sized X-ray CubeSats.
Just a constellation of them looking everywhere?
They could monitor the entire sky continuously in real time, waiting to catch unpredictable, transient events, like a tidal disruption event where a black hole unexpectedly tears a wandering star apart.
Wow.
Or the sudden violent detonation of a supernova. A swarm of CubeSats can pivot and observe those transient phenomena immediately, whereas the big telescopes would miss them entirely because they were locked into observing a different quadrant of the sky.
It opens an entirely new, highly agile, fast-moving chapter in compact astrophysics.
It is a truly staggering technological evolution.
We have gone on an incredible journey to understand this today.
We really have.
We started with the frustrating, impenetrable shield of Earth's atmosphere and the fundamental, almost paradoxical physics of skipping high-energy X-rays like flat stones across a pond.
Right.
We watched astronomical engineers cross completely different scientific disciplines, teaming up with particle accelerator physicists at Spring 8 to literally grow seamless, mathematically perfect metal funnels layer by atomic layer.
Which is still just amazing to me.
We explored the sheer logistical absurdity of building a kilometer-long vacuum tube deep underground just to physically verify the parallel geometry of a fake star.
That 900-meter test.
And then we traveled to the freezing wilderness of the Alaskan Poker Flat Range to strap that nanometer-precise mirror to a suborbital-sounding rocket, surviving the violent 150-decibel acoustic ascent to catch the invisible high-energy scream of a solar flare.
It's an incredible story.
And now we're looking ahead to a horizon where highly affordable fleets of shoebox-sized explorers democratize our access to the extremes of the universe.
It stands as a brilliant testament to human ingenuity and our refusal to accept physical limits.
Absolutely.
But, as we reflect on the specific leap forward in X-ray optics, it raises a profound question that extends far beyond just astronomy.
Oh. What's that?
If scientists can take the massive, highly specialized, impossibly delicate equipment required to observe the universe's most violent high-energy phenomena, and through sheer cross-disciplinary brilliance, miniaturize it to the point where it fits neatly inside a shoebox.
Okay, I see where you're going with this.
What other monumental, seemingly untouchable fields of science are about to experience the exact same revolution?
That is a fascinating thought.
Right. What other massive laboratories, multi-billion-dollar particle colliders, or colossal medical instruments are about to be radically miniaturized, democratized, and placed directly into the hands of everyday researchers, completely changing the pace of global scientific discovery forever?
It really makes you wonder what else we might soon be able to resolve perfectly from a kilometer away down to a single grain of rice.